Okay, this is another day with several pages, so we'll try to be efficient here and hopefully get it done efficiently. Let's see. Take the function 2 to the x. Is this function 1 to 1? Sure, it's 1 to 1. We know it passes the horizontal line test. Passes H line test. When something passes the H line test, when it is 1 to 1, that means the inverse exists. So inverse exists. Functions that are 1 to 1, functions that pass the horizontal line test, have inverse functions. So now we're going to complete a table for f of x so that we can create a table for f inverse. So 2 to the power of negative 2 would be 1/4. 2 to the power of negative 1 is 1/2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4. Think about these ones. What power do you put on 2 that gives you 32? That's 5. You can check it with a calculator or just by multiplying it out. 2 to the 5th equals 32. And then just to make sure that I have a point that actually fits on this graph over here, I'm going to do 8 as an output, which means 3 would be an input. So then when I inverse, when I go for the graph on the other side, when I reverse the x and the y, I'm going to have to go 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, 4, 2, 32, 5, which I don't think is going to fit on the graph, but then 8, 3. Okay, so on the green side, 2 to the x is going to be negative 2 gives 1/4, negative 1 gives 1/2, 0 gives 1, 1 gives 2, 2 gives 4, 5 gives 32, and 3 gives 8. This should not be too much of a shock given our last couple days of school, classes. Over here, when we reverse them, 1/4 gives me negative 2, 1/2 gives me negative 1, 1 gives me 0, 2 gives me 1, 4 gives me 2, 32 gives me 5, and 8 gives me 3. So my graph would look something like this. Okay, so in this graph, our asymptote is where it was before. It's the x-axis, y equals 0. And in this graph, our asymptote is here. It's at x equals 0. This should not be too shocking because we switched y and x. So the y equals 0, you can kind of think of it as becoming this x equals 0. This graph is as if we flipped over, and that's what creates this graph. What is the equation for f inverse? That means we're going to have to do some algebra to undo what has happened. And remember that if f of x equals 2 to the x, y equals 2 to the x, what we're going to do in order to undo both sides is we're going to do what's called a logarithm base 2 of y equals log base 2 of 2 to the x. Cancels. Log base 2 of y equals x. And yeah, I made a little bit of an error there because I usually switch y and x, but I'll just do that now since I forgot to do it up there. But at any rate, we've isolated the y. I kind of solve for the x first. I won't mark you down if you solve for the x first and then switch your x and y, but somewhere it has to happen. That is the name of the f inverse of x. So the logarithm is the way that we undo general exponentiation. The way we undo 2 to the x is log base 2. We learned that in a previous unit, but we did it very gently back there. Now we're just being more formal with it, more formal with our techniques. So what's nice about this is if you need to find the inverse function of 5 to the x, this time I'll follow it in the standard process that we've been doing, is rewrite g of x, y equals f of x, switch x and y, x equals 5 to the y, undo the exponentiation. Log base 5 of x equals log base 5 of 5 to the y, And so therefore, y is all that's left here, and this is log base 5 of x. So g inverse of x is log base 5 of x. Okay, what's the short version of this? Instead of having to do all those steps all the time, unless the problem asks for it, what's the inverse of 17 to the x? That's log base 17 of x. How do you undo log base 4 of x? Well, that's 4 to the power of x. Logarithms and exponentiation undo each other. How do I undo this one with a fancy little shift occurring to it? Let's go see. Y equals 5 to the x plus 1. Switch x and y. X equals 5 to the y plus 1. How do I undo exponentiation? I do the logarithm. So log base 5 of x equals log base 5 of 5 to the y plus 1 is just y plus 1, because that's the purpose of logarithms, is that they undo that exponentiation. Subtract 1 from both sides. Y equals log base 5 of x. Put parentheses around this if there's any confusion at all, but we want to make sure that minus 1 is not considered to be part of our argument in there. And therefore, g inverse is log base 5 of x minus 1. Last example on this page, log base 9 of x minus 2. Log base 9 of x minus 2 would mean, and that's our k of x function, so y equals log base 9 x minus 2. Switch x and y. X equals log base 9 y minus 2. Cancel logarithm by raising both sides 9 to that power, which would yield, put a different color because we're getting into a different part of it, 9 to the x equals y minus 2. Then add 2 to both sides. So y equals 9 to the x plus 2. Final answer, k inverse of x equals 9 to the x plus 2. Happy face. Okay, so this is what we learned at the beginning of the year, or back in the appendix, I think it was. We did a short unit on exponential functions. Now we're learning what are called the logarithm functions. Before we just learned log as an operation. Here we're now thinking of it as a function. It's got inputs and outputs. It's defined the same way as we did things in the past. So y is equal to log base a of x if and only if a to the y equals a to the log base a of x, or x equals a to the y. In my classes, we sometimes treat this as like the dab, right? The upward arrow. The log base a of x equals y is equivalent to the a to the y equals x. So recall that unit from earlier. We have it somewhere else in our notes, and we'll practice it much more as we go through class. So what logarithm means is, what power is it that I put on a that gives me the number x? So we will confirm that these are true using a calculator and changing it into an exponential statement. I don't even think I need a calculator on this one. The exponential statement would be base to the power equals 32. And of course, 2 to the 5th is 32. Let's use our calculator to make sure. Math log base 2 of 32 is indeed the number 5. Here, is it true that 3 to the power of negative 3 equals 1 over 27? Certainly, because 3 cubed is 27. 3 to the negative 3 is the reciprocal of that. So, what would happen in here? Math log base 3 of 1 over 27 does give me negative 3. Change an exponential statement to a logarithm statement. I'm going to take a logarithm to both sides on here. I don't think we learned the ln notation yet. So I'm just going to have to say that this is log base e of e to the 1.2 equals log base e of n. So 1.2 equals log base e of n. Eventually, we'll learn a notation for log base e. We will call that ln. So this will become an ln of n. For this problem, it would be log base radical 5 of 1/5 is equal to x. Log base that number of that number is equal to that number. Example 3, change the logarithmic statement into an exponential statement and then solve. So the way I'm going to teach my classes is to go like this, raise both sides to 3, because that's better than changing to an exponential statement. Cancels, and you get x equals 3 to the 4th, which is 81. X equals 81. Here, this one I probably would do as the power, the exponential form actually. So x to the 2 equals 5, which would mean that x equals, now you might be tempted to say plus or minus 5 here, plus or minus 5, but in our definition, we state that the a has to be larger than 0. So even though the solution to this algebra would be plus or minus rad 5, we only take the positive solution, the radical 5. And then for this last one, it would be 4 to the x equals 4 rad 4. Notice the radical of 4 is 2, right? So 4 times 2, that's actually 8. And then to solve, we can use our techniques and say 4 is the same as 2 squared. 8 is the same as 2 cubed. Take a logarithm to cancel out that exponentiation. 2x equals 3, and x equals 3 halves. Okay, here's an interesting manipulation one. 2 to the x equals 3, we're trying to find out what is 4 to the negative x. Do you agree that 4 to the negative x is the same as 2 squared to the negative x? Because 2 squared is 4? Well, if so, you should also believe that this is the same as 2 to the x to the negative 2. Because by exponent rules, this would be power to power would be negative 2x, and this is just another way of writing negative 2 times x is negative 2x. But what was 2 to the x again? That was 3. So this becomes 3 to the power of negative 2. And 3 to the negative 2 is just 1 over 9. So the answer to that problem would be 1 over 9. Find an exponential function with a horizontal asymptote of y equals negative 3, which contains those 2 points. Okay, to have that horizontal asymptote means that I'm going to definitely need to have a f of x equals, and I'm going to have a minus 3 as my horizontal shift, shifting me down. Okay, 0, negative 2, negative 2, 1. Let's play with this one for a little bit. So if I were to raise something to the power of 0, I would get a 1, but I'm supposed to get a minus 2. So that's fine. That just means I need to put some number here and raise it to the power of x. Because anything to the power of 0 would be 1, and then subtracting 3 would give me negative 2. That's totally fine. Okay, the only challenging part then is to figure out what goes inside of that little hole. And to figure out that, I'm going to have to solve this last piece, which says that f of negative 2, so let's call this one right here question mark. F of negative 2 is question mark to the negative 2 minus 3, and that's supposed to be equal to 1. So question mark to the negative 2 must be equal to 2, which would mean that question mark squared would be equal to 1/2. There we go. Take a square root. Looks like question mark equals 1 over radical 2. So I think the way that I would write my final answer to this, let's do this one in red, would be f of x equals 1 times 1 over radical 2 to the power of x minus 3. Let's make sure this makes sense in that last one. Let's see, 2, put in negative 2, square this be 1/2, square root is 2, 2 minus 3 is, whoops, that's negative 1. Oh man, yeah, made an error. Look at this. If I add 3 to 1, I don't get 2, I get 4. Then this would become not 1/2, but 1/4, and that's a lot prettier. I was wondering why the numbers were a little bit nasty there. This should actually be f of x equals 1/2 to the power of x minus 3. And that fixes it. If I plug in negative 2 now, this becomes a 4. 4 minus 3 is positive 1. That's cool, though. It's okay to make mistakes as long as you always go back and try to figure out where those mistakes came from. So I don't feel too bad. Okay, evaluating logarithmic expressions. Find the exact value without using a calculator. Okay. What power do you put on pi that gives you 1? Of course, that is 0. Anything to the power of 0 equals 1. What power do you put on 3 that gives you negative 27? Answer? Does not exist, right? No matter what powers you put on 3, you never get negative numbers out. Just doesn't make any sense. What power do you put on 5 that'll give you 1/5? What power creates reciprocals? That answer? Negative 1. Down here, what power do you put on negative 3 that gives you 9? Danger! 2 is a correct answer to this, but for logarithms, our base must be positive. The base must be positive. So immediately, because the base is negative 3, this problem is it does not exist. The rest of the answers are on the hub. Let's do a summary of what's going on with logarithmic functions. So with log functions, the domain is since what we're doing with a log is the inverse of the exponential, things literally switch around. So log base a of x is a log function that has an inverse of f inverse of x equals a to the x. The domain here is negative infinity to infinity, so the range here is negative infinity to infinity. The range here was 0 to infinity, so the domain here is 0 to infinity. So it switches the rules of the domain and the range. This is not unusual. We saw the picture at the beginning and we're not shocked. The range looks like it's infinity to negative infinity, and the range or the domain is only from 0 to infinity. The asymptote is the y-axis here. The y-axis, also known as x equals 0. So when we're performing these problems, B, the range, is the easy one to do. The range of this function will be negative infinity to infinity, because the range is always negative infinity to infinity. The domain need to do a little work, because we need to make sure that we're only sticking in positive numbers. So I need 2x plus 5 to be bigger than 0, 2x to be bigger than negative 5, x to be larger than negative 5 halves. So my domain is negative 5 halves up to infinity. Okay. For C, range, that's the easy part. The range is negative infinity to infinity. I might have to think about this one for a moment. Let's think about that one in a minute. Let's do the domain first. The domain would be I need x squared to be bigger than 0. X squared is bigger than 0 almost all the time, right? Everywhere but 0. So this means that the domain would be x not equal to 0, because every number squared is always bigger than 0, except for 0, which is actually equal to 0. So my domain is negative infinity to 0, union 0 to infinity. And no problem with the range. Yep, the range is negative infinity to infinity. My stress, my moment for thinking was because sometimes we have to be careful if we only took part of the graph, then maybe there's some places where you'd go here and then go over here if they were restricted, but that didn't happen here, so it's not an issue. Okay, last page is some class practice. We'll do this in class, of course, but let's do 2 problems from each of these groups so that way we get a little bit of extra practice in here. What power do you put on 5 that gives you 125? 5 cubed is 125. That's how you can get these very quickly. What do I have to do to 1/2 to get to 8? Well, I'd have to cube it. That would give me 1/8. And I'd have to flip it. So I need to cube and flip. And that's -3, right? The 3 is the cubing. The negative is the flipping. Down here, 6 to the power of 1/2 is x. So x is radical 6. Over here, on 12, x to the power of 0 equals 2. What number raised to the power of 0 equals 2? None. So no solution. There is no x to make that one work. And then finally, for our domains, let's do this one. We just need the domain, so I need to make sure that x squared minus 6x is larger than 0. I need x times x minus 6 to be bigger than 0. So make a number line that has a 0 on it and a 6. The graph would be positive, negative, positive, or let's just stick in numbers. Bigger than 6 will be positive. Stick in 1. 1 minus 6 would be negative, and there's positive. So since I need it to be bigger than 0, my domain would be negative infinity to 0, union 6 to infinity. We'll do some more practice in class, and then we will break into some small groups.